Uh, okay. So in this particular session, this section is nothing but a hands-on session on convolutional neural networks. So today only you have learned convolutional neural networks, its applications and its advantages as well, right? For learning the features as well as learning the classifiers together. You might have seen its applications also, several applications. Since last 3 hours, we have been listening to 3 different speakers, and each and every speaker has spoken about the advantages of convolutional neural network, right? So we have seen that convolutional neural network consists of several layers, not like the layers which you have seen in case of traditional neural network, right? Traditional neural network. So let me ask you one question, fundamental question, that given a set of images, why we are interested in solving the problem with the help of convolutional neural network? Why not traditional neural network? What I'm trying to say here is, you are given a set of images, let's say having size 256 cross 256, and is it possible to use a neural network or to train a neural network directly over the images? Is it possible? You have already studied neural network, you have already studied convolutional neural network, which has been specifically designed for image and video centric problems, right? And you have also seen the operations today, the convolution operations, fine. And also you have seen several layers which, right, CNN layer consists of. So now the question is, if an image is given to you, if a set of images are given to you and your task is to design a model, so why are you interested in convolutional neural network, and why not traditional neural network which you have studied? Yes, I'm waiting for your answer. I use neural network, traditional neural network, which you have seen consists of some hidden layers followed by an output layer. There will be one input layer, because there is no label. No, label is given. Label is given. Input images are given. These are input images. X is given. Y is also given. Label is also given with respect to each of the X. Label is also given. And then converts the input data to feature vector, whereas CNN maintains spatial information. Yes, answer is absolutely correct. There are also few other things, right? Any other answers? We'll talk about it. To reduce the trainable parameters, okay? Yes, this is also correct. Let us try to design the neural network first, right? Which we are interested in. So what we know, that the traditional neural network always demands one-dimensional vectors in the input, followed by some hidden layers. So these are, let's say, hidden layer 1, hidden layer 2. This is the input layer. And then you will be having one output layer having neurons equal to the number of classes you are having. Fine. But images are 2D, right? Signals or 2D matrix, right? When it is stored on a computer, sometimes it is even 3D. That's what you all know. So to process these images with the help of traditional neural network, what you have to do is, first you need to convert this 2-dimensional or 3-dimensional matrix into a 1-dimensional vector, right? By converting this 2-dimensional matrix or 3-dimensional matrix into 1-dimensional vector, what you will lose is the spatial information, which is very, very important here. So that means if I take a picture of you, right, through mobile camera, and if I just convert into a particular vector, and if I show you that particular display that pixel values in the form of a vector, probably you won't even recognize yourself, right? Because what we have missed is nothing but the spatial information. That's the neighborhood relationship. It is very, very important here. So this is one of the reason why we are not interested in neural network. Another reason is, let's say, the dimension of the input vector in this case would be 256 into 256. It's around 2 to the power 16. This should be the dimension of the input feature vector, which is really high. Even if you are considering 10 number of hidden, let's say 10 or 100 number of, let's say 100 number of neurons in the first hidden layer, you know what are weights and biases here. So these are all fully connected. So the number of weights possible in this case is nothing but 2 to the power 16 into 100. So these many number of weights we are having only in the first layer. And 2 to the power 16 is a very large number. So that means the number of parameters, right, which are very, very important for us, which is nothing but W, weights, the number of parameters in this case is also going to be very high, right? So there are two things here. One is the complexity is going to be very high. That means the number of trainable parameters is going to be very, very high. And we are also losing the spatial information. That is why we're not interested in directly processing the image through traditional neural network. I hope it is clear. And there is something called as a convolutional neural network, which we have seen earlier, which helps in learning the features as well as learning the parameters of the classifier. And that is why it is very, very popular. And also we have seen the importance of the convolution operation, pooling layers, and activation functions, specifically ReLU and its variants, not the sigmoid and tan sigmoid, because those are saturating activation functions. Fine. Next. Another important point I would like to highlight here is the loss function, the kind of loss function which you are interested in. Let's say you have developed one convolutional neural network, right? Let's say you have developed one convolutional neural network looking like this. And at the end of the convolutional neural network, you will find few fully connected layers. If you go through the literature, you will find the early architectures, especially in AlexNet, AlexNet, LeNet, fine, VZZNet. These are some of the architectures also where you will find, right, multiple number of FC layers. What are FC layers? Fully connected layers or dense layers. So there are some FC layers, and finally, what you will be having is nothing but a classification layer. So this is a classification layer. And you know that the number of neurons, right, or number of nodes in this particular layer is equal to the number of classes. Fine. And what it is ultimately giving and what kind of activation function you are using. We discussed about ReLU activation function, which is a nonlinear activation function, usually used along in the hidden layers in convolutional neural network, right? But what about the output layer? An output layer, what kind of activation function you are using? Can you tell me? An output layer, what kind of activation functions you are using? Yes. Please try to interact throughout the session. What kind of activation functions you are using in the classification layer? And what you are expecting from a classification model? The classification model is not going to give you the label directly. right? The classification model is not going to give you the labels directly. It will give you some value. Yes, I could see some of the correct answers in the chart box by Dr. Manoj, Dr. Binod, right? The softmax function. Softmax activation function is very, very important here, and which is usually used in the as an activation function in the final layer, right? And you know the formula for it. That is e to the power, let's say, e to the power z upon summation of e to the power z, right? So again, let's say I varies from 1 to c, where there are, let's say, c number of classes if you are having a fine, right? So if you want to find out the value, so what kind of value then it will give? It will give the probability value. The probability values with respect to each of the class. Here, each of the node representing one class. Let's say, for example, you are having 10 number of classes. You'll be having 10 number of nodes or neurons in the output layer, and you'll be getting here 10 probability values with respect to each of the class. Then based on the maximum probability, right, we used to decide the class level. Let's say the first neuron is giving value 0.7, the second one is like 0.15, the third one is like 0. Something like say 0.09, the fourth one is like this, right? So we'll be having 10 number of probability values, and if you add them together, it will be equal to 1. So now there might be a question here that why I'm taking exponential here. Can you tell me why I'm taking exponential here? So these are, let's say, like z values, right? You want to find out this probability value. So how to get this? It is like e to the power this value upon the summation of all these values, right? That's fine. So why I'm considering this, e to the power something, can't I directly compute the probability from this z? Yes. A very important question. Why we're interested in softmax? Can't we directly compute the probability values without using this exponential function over here? Yes, we can compute the probability values without this, but there might be some negative values over here. There may be some negative values, there may be some positive values. And what will happen, maybe that negative value, positive value will get cancelled out and you may get some value 0, right? So, but if you are using the softmax function, you are not facing, you are not going to face that kind of problem. That is fine. So what you are ultimately getting from, the value over here, yes, what you're ultimately getting, the probability values over here, that is nothing but a kind of probability distributions we are having. So these are like probability values. And what is given to you, let's say this is X, and what is given to you is the class level. Let's say tiger. Right? Let's say tiger. The corresponding Y value is given to us, which is a tiger. And there are 10 number of classes. Right? And let's say the class number for tiger is 1. Right? And for cat it is 2, for elephant it is 3, like this. So this is what is given to me. Then how would you compute the error? Because you don't know the kind of values, right? You have the kind of coefficients you have chosen with respect to each of the filter, right, is going to give us correct result or not. You may not get correct result initially, but what you know that you can update the parameters of both the classifier as well as the filters. Basically, you can update the coefficients of the filters. So accordingly, you can update the features. So that means what is given to us is an image with respect to one level, that is 1, 2, 3, 4, 5, like this. And you want to find out the error between this probability values and this. You cannot directly compute, right? First, you need to convert these values into its corresponding one-hot encoding. How can I then represent this in the form of one-hot encoding? So I have to write, for the first class, I can write 1, 0, 0, 0, and so on up to 0. For the second class, I can convert in the form of one-hot encoding like this: 0, 1, and rest other values 0. I mean, there are 10 values, of course, here. So what about the third one? 0, 0, 1. The rest of the values will be 0. So what about the last one? It is 0, 0, and then so on up to the last one should be 1. Could you follow? Because whatever you have obtained is nothing but a set of probability values, and you need to first convert these labels into its corresponding one-hot encoding. So now you see, you are having n number of probability values. Of course, we are giving highest because we know the class level. So this value has to be 1, and the rest of the values are going to be 0. But whatever the value you are getting from your model, those are nothing but called as predicted probability values. It's like this one. And now you want to find out the difference between these two. How would you find out the difference between two probability distribution? This is one kind of probability distribution, y cap. This is another probability distribution, y. Right? So we cannot adapt mean square error directly here. But what mean square error says that how much y cap is deviated from y. We're not interested in this. We're interested in finding out the difference between the two probability distribution over here. To find out the difference or the distance between two probability distributions, we have something called as cross entropy. Right? Cross entropy. So you know the formula of the entropy. We also discussed earlier. If you are having only one probability distribution with you, then you can compute something called as entropy. If you are having two probability distributions and you want to compute the distance or the difference between two probability distributions having size same, so then what we have is something called as known as cross entropy, right? It is a concept that has been brought from the concept known as relative entropy. You can find it from the information theory. So what is the formula over here? Yi log of yi cap, where I varies from 1 to c. That is the total number of classes. Yi is the desired value or the target value which is given to us here. Yi cap is the predicted value, right? And this is the formula, cross entropy. So cross entropy is useful when you want to find out the probability distribution, when you want to find out the difference between the two probability distribution, which is happening in case of classification. But in case of regression, your task is to actually find out the error or the loss in terms of mean square error, because at that time you will check how much one value is deviated from another value. In that case, the kind of activation function you will use in the final layer or the output layer is nothing but a linear activation function, right? One question that may come to your mind, that can I use sigmoid activation function at the end? Use sigmoid activation function always at every layer, at every node, you will get a value between 0 to 1. Right? But if you add them together, you are not going to get the probability value 1. You may get the probability value even beyond 1. So that is why sigmoid we are not at all considering in case of multiple classes. But whenever you are having only two classes, let's say there are only two classes, you are having only two classes, at that time, you can use a singular. You can use a single neuron. You can use a single neuron in the final layer, and you can use sigmoid activation function. At that time, the kind of loss function you are going to use is something called as binary cross entropy. Binary cross entropy, and the kind of activation function we are going to use is sigmoid if you are choosing only one neuron in the output layer to solve a binary classification problem. If you want, you can also take two neurons to solve a binary classification problem, but in that case, you have to use softmax and cross entropy. But if you are choosing only one neuron to solve a binary classification problem, then you have to use sigmoid as an activation function and binary cross entropy as the loss function. I hope it is clear, right? That why we are interested in cross entropy for solving classification problem, and what are probability distributions, how to convert the class levels into its corresponding one-hot encoding, and how to choose the activation function in the output layer. This is very, very important. Another important thing, whenever you will compute the error, right, you might have seen somewhere that people are talking sometimes sequential learning strategy, batch-wise learning strategy, or mini batch learning strategy. Have you heard about these terms? Mini batch, batch, sequential. There are three different strategies we use to train the model. And out of them, mini batch is very popular nowadays. Have you heard about these terms? Batch learning, mini batch learning, and stochastic or sequential learning. Even while designing the convolutional neural network, because everyone is using this one, right? Mini batch learning. So you need to also provide the batch size, right? So there are a lot of hyperparameters you will see we need to set by ourselves, right? While training the convolutional neural network model. Can you tell me, have you heard about these terms? And what is the difference between mini batch and batch? Mini batch and batch learning or sequential learning, which one is better and why? Yes. I'm waiting for your response. Shall I discuss this or shall I skip this concept? Okay. Yeah, mini batch. I could see the answers. Mini batch is now very much popular. So what it tells exactly when to update the weights. When to update the weights, right? You can pass one image to the model. You can compute the error. Then you can update the, you can back propagate the errors and update the parameters. That is what is sequential. Batch is you can pass all the images to the model one by one. You'll get the error. You'll get one error, then the second error with respect to the second image, then third error with respect to the third image. Then you will find out the whole. You can just combine all the errors and then you can update the weights. But you need to wait for all the errors to be computed, right? And the first one is probably time-taking one because you need to update the weights and parameters all the time. Mini batch is just like in the middle, right? It has the advantages of both sequential as well as batch-wise learning. So what you will do that you will first divide the data set into small batches. So you'll pass one batch to the model, you will calculate the error for that particular batch, and then you will backpropagate that error, right? You will update the parameters for that particular batch, and then you will continue for different number of batches. Once all the batches are over, let's say you are having 1,000 number of images, training images, and you have set that yes, the batch size will be 100. So there will be 10 number of batches, and you can also say there are 10 number of iterations in one epoch, right? So there are also differences between iteration and epoch. Epoch means when all 1,000 samples are passed to the model. Iteration is when first 100 sample is passed to the model, then it is first iteration, next 100, second iteration. Similarly, you will be having 10 number of iterations with respect to one epoch. So if somebody is asking you how many iterations you are having, so you not also pass check that how many epochs you are having. Let's say you are having 10 number of epochs, or let's say 5 epochs you are having. So you'll be having 50 number of iterations because in every epoch there are 10 number of iterations. So there are different terms which are used in convolutional neural network or in deep learning, so you should know. Now let us directly jump to how to implement a convolutional neural network architecture, especially a sequential convolutional neural network architecture, which you have seen today, similar to AlexNet and VGGNet. Let's say, for example, I have chosen an architecture, right, which a CNN architecture, which will be having multiple layers. The first layer in that in that convolutional neural network will be having 3 cross 3 filters. How many filters? 32 filters. And of course, there are other layers including ReLU and all with it, right? Bayes normalization and ReLU is already there. The second layer is max pooling, where I'm choosing the window size as 2 cross 2, and stride is also 2. And in this case, stride is 1, padding is 0. You know what is padding and what is stride, right? Both are important to decide the output size, right? Or you can say the output volume after convolution operation. I'm again applying, let's say, 3 cross 3 filter. These are the layers, right? Having 64 filters. Again, ReLU is also applied with this, right? Activation. Again, there is a max pool layer. The window size is 2 cross 2 and the stride is also 2. Another one is there is one more layer having size 3 cross 3 and there are 128 filters. And there is one more max pool layer over here. And then I have used a dense layer or fully connected layer which contains 128 neurons followed by a FC layer or dense layer having 3 neurons. Right? So this is what is the architecture and these are input images. I want to implement this. Right? Let's say, for example, the image size which I'm considering is 100 cross 100. And this is what I want to implement. That means I want to develop this model, develop this convolutional neural network model. I'll show you the demonstration actually on TensorFlow platform. But if you want, you can also do the same thing on Keras platform. And PyTorch platform, right? That's not an issue, right? Only the syntax is different. Everything is going to be same. Fine. So now, who can tell me what will be the size after applying 3 cross 3 filter over 100 cross 100 image, and the number of filters is nothing but here 32. Let's say all are 100 cross 100 cross 3. All are like RGB images, right? And the image size is 100 cross 100 cross 3. What will be the size of the feature map, right? The feature map after applying 3 cross 3 filter 32 times. By considering padding value as 0, that means you are not considering any padding over here. If you are not considering any padding, the size is going to be reduced. And the stride is 1 over here, right? So then what will be the size after this layer? Who can say? What will be the size after this layer? Let's try to calculate and tell me. This is very, very important, right? Why I'm saying. So size calculation as well as the parameter calculation at every layer is very important. Because sometimes you may need to develop a lightweight model. You may not have a lot of samples all the time. Right? If you're dealing with medical images, you may not get all the time huge amount of data or huge number of images compared to the natural images. So at that time, you might have to design something called as a lightweight model without compromising the performance. So that means you need to reduce the number of parameters of the model without compromising the performance. So how to do that? So you should also know how to compute the number of parameters, right? Yes. Let's try to answer quickly. What will be the size of the feature map after applying the convolution having size 3 cross 3, and there are 32 filters. Do you know the formula? Do you know how to compute it? Yes. Okay, this is the formula. So then what will be the output? So this is the formula, right? N minus F plus 2P upon S plus 1. So what will be the output then? So it will be 100 minus 3, it is 97. This is going to be 0. This is 1. This is plus 1. So it is going to be 98 cross 98, right? 98 cross 98. This will be the size of the feature map after applying one particular filter. So if you apply one particular filter, you will get a size, feature map having size 98 cross 98. And this filter is actually having size not 3 cross 3, it is actually having size 3 cross 3 cross 3. Right? Because the input is also having size 100 cross 100 cross 3. So this filter, right, having size 3 cross 3, right, will be put over here. So if the input is having size 100 cross 100 cross 3, that means the input image is having 3 number of channels. From convolution, your filter size, the filter depth, or you can say the number of channels in the filter should be same as the number of channels in the input. Although it is not mentioned explicitly, right? But this has to be same. It is written 3 cross 3, but by default it is 3 cross 3 cross 3. And if you are applying 3 cross 3 cross 3 over a 3 cross 3 cross 3 region, right, which is known as a receptive field, right? So over the image, what you will get is nothing but a single feature map having size 98 cross 98. So if you apply 32 number of such filters, what you will get is a 32 such feature map. And what ultimately you are getting is a kind of, 98 cross 98 cross 32. If you are combining them or if you are stacking them together, then what you will get is a 98 cross 98 cross 32. Is the nothing but the size of the feature map after applying 3 cross 3 filter 32 times. Right? That means you are applying 32 3 cross 3 filters over this input image, and what you are getting is nothing but a feature map having size 98 cross 98 cross 32. This 32 is nothing but for the 32 number of filters. So now the next question here is, how would you compute the number of parameters over here? It's very, very important. You should know how to compute the number of parameters. How to know that how many parameters this layer is having? Parameters in this case is nothing but the coefficients, the filter coefficients. You have seen multiple filters yesterday. There are some of filters which are useful in removing the noise. You might have seen median filter, mean filter, average filter, which smoothes the images, the fine details of the image, which smoothen the fine details of the image. You might have seen something called as sharpening filter, which helps in sharpening the fine details of the image. You also have seen some edge detection or edge filters like Sobel, Prewitt and all. So those are like fixed filters. But here we don't want to fix any filter. Rather, we want the model to find out the coefficients, right? But the model to learn the coefficients according to the need, according to the requirement, right? Now the question here is, because at every layer you can compute the number of parameters, there are few layers which contain parameters, there are few layers like max pooling layer doesn't contain any parameter. Those are parameter free layers. Only helps in reducing the dimension of the feature map so that you can reduce the number of parameters in the deeper layers, right? And it has been discussed today itself. So now who can tell me how many parameters are involved in the first convolutional layer? Do you have any idea? Shall I discuss, or I can skip? Yes. The parameter calculation process. The parameter calculation process at every layer. Very, very important. As I mentioned that at every convolutional layer, what you are looking at is nothing but the coefficients of the filters. And those coefficients of the filters are nothing but kind of weights for us. The example is a 3x3 filter I'm considering. So here are the weights. So these are the W's. These are the weights for us. And what you have considered is a 3x3 cross 3 filter. So that means it is a filter having size 3x3 and the depth is also 3. So how many values you'll be having here? 27. You'll be having 27 coefficients. Although it is written 3x3, but I have already mentioned that yes, it has to be right 3x3x3. So this depth and the depth of the input should be equal. So how many coefficients I'll be having? Because it is of 3 dimension and the size is 3x3. So 9 per each dimension, it will be equal to 27. So 27 weights, right? You can say parameters with respect to one filter. So how many filters we are having? We are having 2 filters. So we'll multiply 27 with 32, and every filter is associated with a bias, right? Every filter is associated with a bias over here. Plus 32. So 27 plus into 32 is the number of parameters we have. Plus 32 is nothing but for the bias. These are weights or coefficients, and these are bias. So altogether, these are nothing but parameters. And if you compute, probably the value will be, if you multiply 27 into 32 plus 32, so you'll be getting the value equal to 896. We'll check, right? Coding, we will check whether we are getting these many number of parameters or not. So now you can just tell me the size after using max pooling, where the size is 2x2. That means the window size is 2x2 when the stride is 2. So that means you will exactly get, right, an output which is the half of the output which you have got after the convolution operation. That means I can directly write the answer over here, which is 49 cross 49 cross 32. Max pooling doesn't affect the value of the depth, right? That means the channel will remain same even after applying max pooling. It is only helping to reduce the dimension, the spatial dimensions, right? Previously it was 98, 98. Now it is, because you are taking the stride value as 2 and you have chosen the window size 2x2. So that means you will get exactly the half of this image. That means which is 49 cross 49 cross 32. Again, if I ask you to apply a 3x3 filter over here, so how would you do that? How would you do that? 3x3 filter. I have written only 3x3 filter, but you know what should be the size of, because you are applying this filter over this input. So what should be the size of the filter? The size of the filter is actually 3x3x32. So the filter depth should be equal to the depth of the input. Then only you can perform convolution. That's what you know, right? So this should be actually, although it is not written explicitly, but you should know that the depth of this filter should be equal to 32. Right? So that means this many number of parameters, right, that a single filter may contain. And then you are having 64 filters over here. You can just multiply 3 into 32, multiply by 64 plus 64 for bias is nothing but the total number of parameters you are having in this particular layer. I hope it is clear, right? And you can use this concept, right, whenever it is required to compute the number of parameters, right, in convolutional neural networks. So if you know how to compute the number of parameters, if you know how to compute the size after performing convolution operation, max pooling operation, probably you can design your own convolutional neural network you may not find any difficulty in understanding any architecture which is there in the literature. It's very, very important, right? So if you go through the literature, you will find people have used, right, only a single type of filters, right, just after. I mean, that concept actually was first proposed in VGGNet architecture. If you go through the AlexNet architecture, you will find people have used multiple types of filters, right? I mean, the filters having varying sizes, right? You will find the filters having size 11 cross 11. You will find filters having size 7 cross 7, 5 cross 5, even 3 cross 3. In BGG, right, they have mentioned the usage of 3 cross 3, right? Why do we need only 3 cross 3 filters? Because even using 3 cross 3 filters, if you are using 3 cross 3 filters multiple times, you can also get the same impact, right? Let's say if you are applying 3 cross 3 filter 2 times, so you can have the same impact whatever you are having with 5 cross 5. So you can just repeat sequentially 3 cross 3 filter, right? But at the same time, by doing this, you can also reduce the number of parameters. Instead of using 5 cross 5 filter, you can use 2 3 cross 3 filters sequentially, right? So the receptive field size in this case is 5 cross 5. In this case also, it is going to be 5 cross 5. So that means both are going to be same. And the number of parameters in this case is nothing but 9 plus 9 is 18. In this case, it is 25. And if you just enlarge the size here, 7 cross 7, in that case, you can repeat 3 cross 3 filters. And that time, there will be 27 number of parameters required for 3 cross 3 filters sequentially. Even you are increasing the depth. There are multiple benefits here. You are increasing the depth of the, but the depth of the architecture. At the same time, you are reducing the number of parameters. And if you are choosing 7 cross 7, you will get 949 parameters. You see, we are using 3 cross 3 cross 32 is the filter size, right? So accordingly, you can see how many parameters you can reduce. So if you're planning to design the lightweight models, you can just think about using 3 cross 3 filters, right? To have the same impact of 5 cross 5 and all. So in GoogleNet also, you will see that people are not only using a single type of filters over an input I, they're also using different types of filters. That means filters having different sizes are being applied over the same image to extract multiple informations or you can say that to extract informations at different scales, right? At different scales. You can also think about designing such a lightweight model through which you can extract informations from the input at different scales. Very, very important for few applications where the objects varies. Where the object is having different shapes or different sizes. In that case, also you can think about applying this kind of what I can say concepts, right? One thing I think I forgot to mention that when I was discussing that why we are not preferring neural network and neural network is also, if you are using neural network that you are going to lose spatial information at the same time, the number of parameters is going to be very, very high. So now you can tell me, because we all know that convolutional neural network also demands huge amount of parameters in terms of millions. Like in case of, AlexNet, it is 60 million, 60 million. In case of VGGNet, it is 138 million and then you will find that GoogleNet, right? In case of GoogleNet, it is only 5 million and all because they have not used any fully connected layer at the end, right? So nowadays, not many fully connected layers are being used at the end because fully connected layers, you also know what is the disadvantage of using fully connected layer at the end. Even so many number of fully connected layers may lead to huge number of parameters, right? So the parameter complexity is going to be high. Now, can you tell me how then convolutional neural network is going to help us in this case to reduce the parameters? Because we know the convolutional neural network takes a lot of parameters. Yes, in case of convolution, right? In case of convolutional neural network, this is going to be correct. So spatial information is going to be preserved, but can it helps in reducing the parameters compared to the traditional neural network? You can see one thing here that in traditional neural network, every neuron, right, in the hidden layer is associated with every other neuron in the preceding layer. But in case of convolutional neural network, you have just now seen that every hidden neuron, let's say this is the feature map and this is the hidden neuron here, is only connected to a small portion of the image, the local receptive field. It is not focusing on all the positions in the image. It is only focusing on a small part in the image. That is how we reduce the parameters. At the same time, we are applying the same filter over every pixel of the image, right? And that is how actually we reduce the number of parameters, right? In case of convolutional neural network compared to traditional neural network. Fine. Now let me show you some of the demonstrations. Yeah. So we'll see how we can design a convolutional neural network, right, on TensorFlow and Keras platform. Yes, as you all know that you need to first, because I'm using Google Colab platform, so you need to first mount with the Google Drive because my data is present on the drive, on my drive. And here are some of the, you can see here are some of the libraries that you need to import, right? TensorFlow, NumPy, Matplotlib for plotting and all, right? OpenCV to read the image, to display the image and all. So fortunately, the dataset which I'm considering has already provided me, has provided the official splitting. That means I'm having one train set and one test set, right? That means you need not to split the data set, right, further into training and test, because training testing is given to us. Yes, validation, if you want, you can just convert the train set into train and validation. Validation is very, very important. Also helps in reducing or in overcoming the overfitting issue or the overtraining problem. Also, validation is very important to find out the optimal parameters of the model, right? That is what we have not discussed, validation. But if you want, you can just apply some strategy, or you can say the same stratified random split strategy over the training set to derive one validation set, right? So validation set again is a part of training. It's not a part of testing. Testing is very different. Testing will be only used to evaluate the model, the performance of the model. But validation will guide the training process, right? So validation will guide the training process. Sometimes it may so happen that if you train the model, what we always feel that if we train the model for multiple times, the model is going to be, always provide us good results. Yes, it happens during training. The model is going to give you good results, right? If you are training, if you train the model, right, for number of iterations, the training error is going to, this is a training error, right? This is training error. The model is going to perform well on the training set. That means the more you train the model, right, the model may perform well on the training set, but there's a possibility that the validation, this is a validation curve, right? The validation error starts increasing, right, after some point of time because of the overfitting issues, right? What does it mean? Especially what I'm trying to say, this is validation error and this is training error. The more you train the model, the training error is going to be good, but there is no guarantee that the validation error is always going to be good. That means the test error is going to be always good, right? So that means a model may perform well on the train set, may or may not perform well on the test set. If you are experiencing or encountering this kind of situation, so this situation is known as overfitting situation. The model is performing well on the train set, but not performing well on the test set. In that scenario, what you can do, you can stop the training process whenever it is required. That means when you stop the training process, and what we call it as early stopping. We call it as early stopping. That means you need to stop the training process at some point of time. You should not train the model more and more. If you train the model more and more, the model may become complex. The model may fit to some of the noisy samples, right? So then what you have to do, you need to also look at the validation error parallelly. And then you have to check that here you can see to the training error is going down, the validation is also going down. But there may be some point where the validation error may increase. That is actually the right point to stop the training process, because if you train the model more here, the validation error is going to be high. That means the training error is going to be high. So that means you need to stop the training process here. And this process is also known as overtraining, and it happens also sometimes, right? Overtraining in practical applications also, right? When we teach, I mean, the students, right? Even for a long time, let's say, so that also happens, right? So during training, yes, he or she will perform well, but may not perform well during the final examination. So called as overtraining, right? So we need to also identify that situation, right? Then that is where actually validation is going to help us, right? So validation here is going to help us to decide when to stop the training process. That means what should be the optimal parameters of the W and B, that is the weights and the bias. Fine. Let's again go back to coding session. I'll share the code. No need to worry about it, right? So once you will, then what you will do? This is the path where the train set and test set is given in the form of a folder. Then you need to load the folder. If you want, you can just read the image. You can display some of the images over here. You can see, and then there are different settings, for the data loaders. If you want, you can normalize the image, divide the pixels of the image by 255 to make the pixel values from 0 to 1, very useful sometimes, right? And then if you directly want to read the images which is present in the directory, right? So you can directly use this function, right? That is train data gen, which is nothing but where you have stored the trend data and where you have stored the normalized trend data. So flow from the directory is nothing but the data loader. That means you want to load the data from the directory, right? And this is where you can pass also few things like what should be the size of the input, what should be the base size, and the class mode is categorical over here. Similarly, you can also do the same thing for the test set. There's no validation set here, but if you want, you can just split the train into train and validation, right? Which is very, very important. So you have to also use validation whenever it is required. This is actually the important one. This is actually the code to design the CNN architecture, which I have just now explained. If you see, the same thing is written over here, right? It is very, very easy to call a function known as convolution 2D. Con2D is a function which is already available in Keras layers. You have to only call the function, pass the parameters carefully. This is the first layer I already mentioned, having 32 filters. You need to mention the number of filters, the size of the filter, the kind of activation function which we are going to apply after the convolution, and what is the size of the input, which is nothing but 100 cross 100 cross 3 over here. Then I've used a max pooling layer, having, I'm passing 2 cross 2 means the size, window size is 2 cross 2, right? Sometimes people call it as a filter size, which is 2 cross 2, and 2 is nothing but here the stride, right? So there are two things. Again, I'm applying, another 3 cross 3 filter. If you remember if you remember the diagram, 3 cross 3 followed by max pooling, again 3 cross 3 followed by max pooling, 3 cross 3 followed by max pooling, followed by FC layer, and then followed by another FC layer containing 3 neurons, because we are dealing with such a data set which contains 3 neurons, especially three classes, right? That is COVID-19, pneumonia, and normal. You can see over here how easy it is just to create one convolutional neural network here, just by calling the functions whatever is available, right? Convolution, max pooling, convolution, max pooling, right? Flattening is just to, because you want to pass the output of the last convolutional layer. We do not mention, yes, we are mentioning here, this 32 is nothing but the filter here. The 32 is nothing but the filter, 64 is nothing but the filter, 128 is nothing but the filter here. We're mentioning here the number of filters. This 3 cross 3 is nothing but the size of the filter. It could be 3 comma 3, it could be 5 comma 5, 7 cross 7, anything, right? A ReLU is the activation function, you know that. Fine. We're mentioning over here. So and at the end, what I'm doing, what I'm trying to do here is flattening. So that means I'm trying to convert this 3-dimensional volume output, whatever I'm getting over here, after the last, layer here, especially, right? And then I'm trying to apply fully connected layer. So either I can apply here a global average pooling layer, right? Or I can just flatten the matrix, whatever is the output after this max pooling layer, so that this will convert into a one-dimensional vector, right? And then you can use a FC layer for further processing. Either you can use a global average pooling layer, or you can use a flatten layer over here. That also you need to check that which one is better, right? Flatten is going to give you a very high dimensional vector. Global average pooling is going to give you a dimension equal to 128, because max pooling is not going to reduce the number of channels. So for every channel, you will get a single value. So that means you will get a 128 dimensional feature vector over here, right? After applying global average pooling. So both things are acceptable. So you need to check which one is giving good results. I think you still remember, right? So this is exactly the architecture which I discussed right here. And I think you still remember the size which we computed, that is 98 cross 98 cross 32 after the first layer. You can see over here, the size after using the first convolutional layer is 98 cross 98 cross 32. And also I mentioned that the size is equal to, sorry, the number of parameters is equal to 896. If you still remember, it is 8096 I've mentioned over here. You look at here. I mentioned 896, and you know how to compute it, right? See, so if you just write here model.summary, so summary is the function, and model is nothing but the name, right, of the model which you have given here. So dot summary is the function. If you just write it out, so then it will give you the shape, especially the output shape after each layer, and the number of learnable parameters required at each layer. So at the end, you will find how many number of parameters we are having and how many number of trainable parameters we are having, right? So then you can, so once you will design this architecture, what is your task? Is to build the training setup. So how to build the training setup? That means at that time you need to decide what kind of loss function you are going to use, what kind of optimizer you are going to use, whether it is stochastic gradient descent, whether it is RMS prop or ADAM and all. ADAM is very popular. There's another variant of ADAM which is recently available. I mean, recently proposed, known as ADAM W. That also you can explore. So here I'm using categorical cross entropy because I'm going to deal with multiple number of classes. I mean, it is beyond 2, that means 3. So that's why I'm using this. If you want, you can also give the learning rate, right? So there are multiple things which you can provide here. Learning rate also can be provided over here. And then what you have to do, I have to decide the number of epochs, as I mentioned earlier. And then you need to write this. This is a very powerful function, that model.fit. The model which you have already built, you want to train the model. So while training, as you all know, that we need to provide both train data. If you don't have validation data, then you should not provide. But here in this case, because there is no validation set, I've taken the test data, but you should not consider, this is wrong. You should not consider test data is the validation set, right? Test data is the validation data. Just to show you, right, that how to pass both the train data and validation data in the fit function, I've just taken it, but it should not be the test data. It should be always the validation data. Otherwise, you should not take it, right? Otherwise, you can only take the train data. Your train data means obviously X and Y, because you want to pass X and Y to the model. And what is the model? The model you have already defined. This is the architecture of the model, and these are the parameters of the model, right? You can say the hyperparameters of the model. These are hyperparameters, not trainable. So parameters are trainable, hyperparameters are not trainable, which you are fixing. Fine. Then what you will do? So obviously, if you run this code, you will see, right, that yes, your model is training, and you will also find that because the model is trained not properly here. So actually, I was taking, I think I have taken 25 epochs, but later I have modified to 5 just to show you, because it takes a lot of time, right? So then you can see over here the loss is gradually decreasing, right, after each epoch, but still it is not acceptable. You need to further, train the model. You can see over here. So this is the graph, convergence graph. Especially this graph is very important. The loss graph, loss convergence graph after each epoch over the training set and the validation set. That also you need to check whether the graph is converged or not, right? That means if you find that the loss is not changing, right, over 2 to 3 epochs or 5 epochs, right, at the end, so then you can say yes, your graph is converged. So that means you can stop the training process. Then you can test the model. And for testing the model, there are different evaluation measures we have, like confusion matrix for classification. So you can also apply the same function over here to compute the confusion matrix, and there are several different types of metrics we can compute from it. Fine. So another implementation I would like to highlight, because for transfer learning, I would definitely discuss the transfer learning part in the next hands-on session, because we are running out of the time. So let me also show you another architecture if you want to really implement any architecture which is given to us. Let's say ResNet, or whether it is DenseNet, whether it is VGCNet and all. So what you will do? So this is actually one of the architecture we proposed, right, in the year 2022 in IEEE Journal of Biomedical and Health Informatics. So during that pandemic time, we also developed few algorithms. Especially, we have developed some lightweight, multi-scale feature learning convolutional neural network right? So the goal was to also design a lightweight model at the same time to also extract or learn multi-scale informations using only 3x3 filters, not using 5x5, 7x7, 3x3. So you know that yes, we can use 3x3 filters sequentially to have the same impact of 5x5. You can see over here, right? So what I have done, so this is not actually a plus operation over here, although it is extensively used this notation for addition, but here it is actually a concatenation operation. You can see over here. So there are two 3x3 layers here, and there is one 3x3 layer, and the outputs are concatenated, followed by a 1x1 convolution, and there is one more 3x3 convolution over here, and there is one more 3x3 convolution, which is again concatenated over here. And there's a 1x1 layer. So I mean I don't have time to get into all the details how it is helping in extracting the multi-scale informations. But if you want, you can just go through our paper. The code is also available. I can also share code with you, right? So if you want to actually implement, let's say, this module, right? And this module has been repeated over several times over here, right? If you want to just implement this module, how to do this? So yes, this is the input, and you can just pass two convolutional layers over here. Then you can pass another convolutional layer over the same input. Just concatenate their results. I'll show you the demonstrations over here. Other steps are same only. If you want, you can also perform some augmentations over there. I also discussed about augmentations in the last class, right? So these are some of the possible augmentations you can do, like flipping and several others, rotation, scaling, and all. Very, very important, the affine transformations for augmentation. This is the, you see, this is actually, I think, yeah, this is MFL block, right? This is the code. Implement, right, that particular block which I have shown to you. So mini block means it is just a collection of 3x3 followed by batch normalization and ReLU. You see, that is what is known as mini block. So you know that this is, if this is input, over input we have applied two things, right? One is so double mini block is like where there are two convolution, 3x3 convolutions are applied. So you know that from this block that sometimes there are two 3x3 blocks over here. There's one 3x3 block over here. So two 3x3 block over the input, one 3x3 block over the input, and then you need to just concatenate them. You see here, concatenation has been met using concatenate function, right? So both are having same output, the size is same at the same time, right? So you can just concatenate them together. So then there is a 1x1 convolution you can see over here, which is applied over the concatenated output. You can see over here, over the concatenated output, there is a 1x1 convolution followed by a mini block. We are calling it as a mini block over here, right? So you can see how we have written the code. You can see 1x1 followed by a mini block. Again, there is one more mini block over here, which is applied over the input. So this, you can see over here. So this mini block is just applied over the input and again concatenated with this. And there's followed by 1x1. If you want, again, you can use a, what I can say, residual connection over here. So residual connection, if you want, you can insert a residual connection where you can add the output here, add the output with the input. If the size of both input and the output is same, then only you can perform here, an operation known as, we can say residual operation over here, right? Which is available in or introduced in ResNet, right? Residual networks. And you will also find its application everywhere. The residual connections are very, very important, right? Even in transformers also, you will find modern day transformers, you'll find its applications. So that means after just getting this output, let's say conv is the final output. If you want to apply a residual connection over here, so then what you have to do is you can just write the output is equal to conv plus input. That is what is the residual connection. So this is how actually you can just implement it. And this is the whole architecture. You can see just we have used several functions because functions are really useful, right? To write the codes, and it is very easy, right? So no need to write the 3x3 3 times here. So we have just written the 3x3 filter over here. We have defined in a mini block, and we have defined a double mini block which contains two number of 3x3 block, which always follows a base normalization and a ReLU activation. And then this is the whole architecture which we proposed. And you can see over here we are considering ADAM as an optimizer having the learning rate 0.001. And through this model, we have got interesting results. And if you now look at the number of parameters it contains, so the number of parameters or the number of learnable parameters are close to sorry, it is close to, you can see over here, it is very, very less. It is, I think, 0.7 million, right? So it is less than 1 million, you can say that. With this, architecture, we have obtained improved performance compared to the architectures that was available at that time, right? I mean, compared to the state-of-the-art CNN architectures. So this is how actually, you can implement the CNN architecture. So we are running actually out of time, so I cannot discuss all these things, but I will share the code with you. I hope at least you got the idea behind, right, the convolutional neural network, how to implement it on the TensorFlow platform. You can also do the same using PyTorch platform, not an issue, but only the syntax is going to be different. All rest of the steps are going to be same, right? So again, yes, you can find out some of the results over here, results of the training. Yeah, something very different over here. Not a problem. Okay, so I'll stop here. If you're having any queries, so you can just discuss. So if you are having any queries, you can just write in the chat box. Or else you can drop an email to me, right, if you are having any queries. I'll wait for 1 minute. If you are having any queries, I'll be happy to answer. Yeah, I will share the source code, definitely. Any other queries you have? Yeah, I think there are no queries, so we can stop here. Thank you very much for attending all the sessions. I would again request to all of you that please attend all the sessions tomorrow. Even more important, right? You'll get to know about it. So tomorrow we'll be having sessions on attention mechanisms. Or transfer learning has been covered already, but attention mechanism is very, very important here, and followed by RNN and LSTM, which is also useful, right, for many applications, many image and video processing applications. Today also we have seen its importance, right? So thank you very much. Good night. See you tomorrow.